Okay, so this lecture is all about cryptocurrency with an emphasis on Bitcoin. So I'm going to start with a little bit of an overview of money, some of the constraints on money, that sort of stuff. Then I'm going to talk about, do a little bit of a refresher on hash functions and digital signatures. So I covered all this in an earlier lecture, but I'm just going to bring it back into your minds because you can't understand Bitcoin without understanding hash functions and digital signatures. So let's start with money. So these are some of the classical properties of money that economists talk about. So it's a medium of exchange. So, back in the day, if you wanted to buy a nice pair of shoes from the local shop, you have to take your, some of your produce along to the local shop and exchange it for those pair of shoes. So you might have to take along one of your sheep and give them, half the sheep maybe in exchange for the new pair of shoes. This is a little bit inconvenient, and maybe the person who was selling the shoes didn't really need any sheep at that particular point in time. But with money, we have a sort of a generally accepted way in which we can exchange goods that avoids this problem of barter. So instead of giving this man with the shoes half of my sheep, I give him some money, and then he can then exchange that money for someone else, with someone else, for whatever he happens to need. So it's a unit of account as well, so enables us to run modern businesses, I guess. We can track how much we're gaining and losing in our business. So the man, who exchanges his shoes for half of my sheep, and then he exchanges that sheep for something else. He doesn't have any real way of tracking how well, he's doing, what his assets are, what his liabilities are, and so on and so forth. Store of value is another sort of really crucial aspect of money. So generally money lasts for a while. It's built of fairly durable stuff. Whereas if I buy the shoes and give the man half a sheep, then that half a sheep is going to be pretty rotten within a week or two. And so all of the effort he put into the shoes, which he then gave to me and received in turn this sheep, all that sort of value stored in that sheep will just rot away into nothing within a week or two unless you can store it or exchange it quickly for something else. Whereas money is a very convenient way in which you can store value and then retrieve it at a later point in time. So crucial features of money: it has to be scarce but not too scarce. If there's too much of it, you get these problems with inflation, which I'll talk about. And it has to be trusted, right? If I buy the shoes and give this man, a pile of sand or whatever, then that's the problem, that it's not really scarce enough because he could just go off and get a pile of sand from the beach. Or if I give him some notes that I've drawn by hand myself, then, how does he check or establish the authenticity of that? Because he needs to be able to, what I give him in exchange for the shoes, he needs to be able to give to someone else in exchange for something else. So it has to be generally trusted by everyone who's using the currency. So I'll give you a few examples. So got gold, classic one, used probably throughout history. It's scarce, it's kind of tricky to get hold of, but not too scarce. It's fairly easy to verify its authenticity. You can bite it, do chemical tests, density tests, and so on. And it's pretty durable. It's a good store of value. Then we've got cowrie shells used in parts of Africa, and other shell currencies being used elsewhere. They're really tricky to fake, right? Because they're very detailed, kind of small and convenient. That's also a nice feature of money. And then we've got kind of paper currency issued by banks and so on. So over the years, many currencies have been minted directly from gold or silver. So in this case, the coin is like what's written on it corresponds to the weight of it, if you like. So I think like a pound, back in the day would have actually weighed a pound, and would have been a pound of gold kind of thing. Nice thing about gold and silver currencies is that their validity can be easily tested, right? If people bit gold, check it's soft, not some kind of alloy or something. Density tests, chemical tests, and so on. And the same is true of cowrie shells, as I said. They're pretty hard to fake. You need to be an absolute expert porcelain manufacturer to produce a plausible cowrie shell, and even then, take more effort than it was worth, probably. So back in the day, the paper currency was tied to the gold standard. So what that meant is that the bank held the enormous pile of gold, and they issued paper that corresponded to that gold that was held in the bank. So my £1 paper note, I could actually take to the bank and say, well, let me have my gold, please. And the bank would pop into the guy would like pop into the vault, pull out a pound of gold, and then give that over to me. So the paper currency was really just a representation, a more convenient way of exchanging the gold that was in the bank. But it collapsed, probably because, well, partly because, gold production did not match economic growth. So in an economy, you need lots of exchanges. If you economy based on money, you need to constantly exchange money, and you need more and more money if you've got more and more economic activity. If you're only sort of selling one sheep a year, then you don't need much money in order to sell that sheep. But if you're selling lots of sheep and buying houses and buying ships and digging holes in the ground, whatever, all of this requires a much greater exchange of money. And if they haven't got enough money, physical coins to do that, then you've got to go and find something else. So you can't base your paper currency on gold if you haven't got enough gold for the economic circulation that you need. So after the gold standard collapsed, almost every major economy has issued paper currency instead. And the value of the paper currency depends on the belief that the government or central bank will not increase the supply of banknotes too rapidly. And so two things. So the central bank or government has to limit the supply. Otherwise, you get this inflation. Like today, my sheep is worth £5. Tomorrow, it's worth £10, and you get this escalating, increase in currency, which I'll talk about, hyperinflation. And you also need to prosecute people who produce counterfeit currency. There needs to be some way of establishing authenticity of the currency so that it can be publicly trusted. So this is what you get if the government doesn't limit the supply of currency and just prints and prints and prints and prints more money. During the time of the gold standard, they couldn't do this because the currency was linked to a fixed amount of gold. But once it's no longer tied to gold, they can print as much as they like. And if they don't do that carefully, you get this hyperinflation that you get in Germany after the war. That man's probably off to buy a pint of milk or something. And then more recently in Zimbabwe, had a similar problem. Chap off the supermarket, get a loaf of bread or whatever. So here's $100 trillion. The government keeps printing money so that it can pay its expenses, but then because that increases the supply of money, the wages go up, and then that increases the prices of goods, and then the wages go up, and so on and so forth. So it's a vicious cycle in which no one really benefits. So that's a sort of very quick, overview of money. I mean, I'm no economist, but that's the rough picture, I think. And then we get onto the electronic exchange of currency. So, back in the day, people swap bits of gold and bits of sheep for things. But in the modern age, we do a lot of our currency exchange electronically. And this is all done, using a trusted third party. So if Alice wants to pay £50 to Bob, she sends her credit card details to Bob. Bob contacts the bank. The bank, checks that Alice has the money, shifts that £50 from Alice's account to Bob's account, and then Bob checks that the transaction has taken place by checking his account, and then he can send the money, the goods to Alice. So Alice wants to buy a hat online, let's say. The bank does the transition of funds, and because both Alice and Bob trust the bank, they both check that the funds transition has taken place, and then Bob will send the hat to Alice. And in this lecture, we're going to talk about cryptocurrency. And cryptocurrency, it's a large-scale, peer-to-peer internet-based application. And I'm going to focus on Bitcoin here. And as I say later, there's lots of second-generation cryptocurrencies, but Bitcoin is the really big, successful one. So I'm going to explain how Bitcoin produces a form of money that's limited in supply, can't be faked, and doesn't rely on a third party for its verification, and it can be used to spend money online. So I strongly recommend that you read the original paper on Bitcoin, which is on the course website, because it's an absolute piece of genius, Bitcoin, I have to say. Okay, but before we get into Bitcoin, I have to do a little bit of a refresher on hash functions, digital signatures, because you can't understand Bitcoin and cryptocurrency without understanding this. And I'm sure you assiduously watched the lecture on this before the peer-to-peer network lecture, but I'm just going to refresh it all now. Okay, so public-private key cryptography. Alice has a large random number, or key generation program finds a large random number, and generates two keys, a public key and a private key. So anything that's encrypted with a public key can only be decrypted with a private key, and the other way around. So anything that's encrypted with a private key can only be decrypted with the public key. So and the keys are related, but you can't get one key from the other. If you know the public key, you can't find the private key, and vice versa. So encrypt with one, decrypt the other, but you can't. If you encrypt with the public, you can't decrypt the public, and vice versa. So if you want to send messages, Bob can encrypt with Alice's public key, and now the message can only be decrypted with a private key, so only Alice can receive it. So she can distribute her public key and use her private key to read her messages without, and no one else can. Then hash functions, they map data of an arbitrary size to data of a fixed size, and lots of different algorithms have been designed for this. So here we have, different strings, feeding them into a hash function, and then we're getting these fixed size chunks of data coming out the other side. Then cryptographic hash functions are sort of special case of hash functions. They're impossible to invert, so if you know this bit of data, you're not going to be able to find this bit of data. So you can't invert, you can't calculate the original data from the hash. They're very sensitive to changes in the data, so only if the data is identical will you get an identical hash. And no two messages will have the same hash. And so, SHA-1 was a popular cryptographic hash function. I think it's become SHA-256 maybe. So we have different inputs, and these inputs are very subtly different sometimes. So in this case, we're missing a single V. But these very subtly different inputs lead to radically different outputs. You can see these two hashes are completely different. So sensitive to changes in the data, there's a unique mapping, so even a slightly different data will lead to very different digest. And then if you know the digest, you're not going to get anywhere in terms of trying to figure out what the hash is, except by a sort of a very costly brute force search. Yep, okay. With hash functions, you get this feature of collisions. Collision is when you've got two inputs lead to the same hash value. So in the previous lecture on hash functions, I talked about this very simple hash function where you sort of add up the ASCII values and then take the modulus. And in this case, cat and act have exactly the same hash function. So that's a collision because you're not mapping, there's not a unique mapping between the input and the output. Cryptographic hash functions are very collision resistant, and so it's very hard to find two different strings that lead to the same hash value. So it's hard to find SHA1x equals to SHA1y, where x is not equal to y. Two different y, x and y are different and lead to the same hash, not very likely. I think you need like 2 to the 160 tries of different y values until you get the same output for a given x value. So you could do a brute force, so there's a chance, but a very small chance of collision in cryptographic hash functions. But what you can get is partial hash collision. So that's a value of y whose hash matches the first k bits of the hash of x. So suppose the hash of x equals blah, 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 and the hash of y equals blah, 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 blah. So the two hashes are different, viewed globally, but the first 8 bits of the hashes are the same. So we've got a partial hash collision. It's not a problem for the cryptographic hash function, but it's a sort of, it's a feature, and that feature is going to be, I'm going to discuss in relationship to Bitcoin. So there's an 8-bit partial hash collision here. And for small key, so it's easy to find small overlaps in the hashes of particular strings or whatever. It's very hard to find, and it gets increasingly hard to find increasingly longer matches between two hashes. And then finally, digital signatures, which is a big part of Bitcoin. So this is important for Bitcoin, as I'll explain later, and digital signatures are very important for Bitcoin. So to sign a message digitally, we take a hash and produce a digest, and we encrypt this with the private key of the person who's signing it to produce a digital signature, and we put that digital signature in with the message. So this is to sign the message. So Alice has her public and private keys. Here we have the message. CCE 310 is a fantastic class. It gave me hope for humanity and changed my life forever. So, very accurate to the point message. We take the hash, and here's our hash here. And then we use the private key to encrypt the hash. So this is the encrypted hash, and that is the digital signature. So when Alice sends the message, she sends the plain text message, let's say, because it's not encrypted, it's just signed. So the message and the signed and the signature of the message. Now to check that it was Alice who sent the message and that the message hasn't been tampered with, what people do is they decrypt the signature using the public key. And if the decrypted signature matches the hash of the message, then it's from the sender. And this also prevents tampering the message, which alter the hash. So Bob has received this message. He takes the signature, uses Alice's public key. Remember, it's been encrypted with the private key, so it can only be decrypted with the public keys. Only Alice's public key can be used to decrypt this, and she can make this all available to anyone who wants to check the signature. So she sends her key out to Bob. Bob uses the public key to decrypt the signature, and that gives the hash of the original message that Alice sent and encrypted. Bob also has the message, the text of the message, and so he can take a hash of that. And so if the message hasn't been changed, the hash of the message should match the decrypted hash of the message, right? There should be an exact match here. On the other hand, if the message has been changed just a tiny bit, as we saw with cryptographic hash functions, that's going to lead to a radically different hash here. There'll be a mismatch here, and therefore we can tell the message has been changed. And if it doesn't, and if uses the wrong key or not a key that's not Alice's public key to decrypt it, then obviously the decrypted hash is going to be kind of senseless, and it's not going to match up with the hash of the message. If there's a match, we can tell that it's Alice that sent the message, and that the message hasn't been changed. Okay, so now I think we've got enough in place to talk about how Bitcoin works, so that's what I'm going to cover. So this is like the first algorithmic currency invented by someone called Satoshi Nakamoto. There's an Australian guy whose name escapes me who claims to be Satoshi Nakamoto, and the BBC were like, lovingly, celebrating his achievements and all that. But there are other articles saying, well, actually, this guy's claimed to be Nakamoto before, and it's still a little bit open who is really Satoshi Nakamoto. But it doesn't really matter because it's a brilliant paper and it's a very clever system, and I like it a lot, I have to say. So algorithmic currency, so as I said before, read the original paper on this because it goes into it extremely clearly, and this is really just a summary of what went into that paper. So Bitcoin enables electronic payments over communication channels without a trusted third party such as a bank. That's kind of what Satoshi was kind of aiming at with this system. He didn't want the payments to be verified by a bank, so he wanted a currency that could be spent online, but also trusted and couldn't be spent. So it's based on a peer-to-peer network, and the issue of currency and the verification of transactions is controlled by the execution of a hard computational task. That both limits the supply and limits people's ability to manipulate or fake currency in the network. And so no government or central authority can manipulate the supply of bitcoins. As I'll explain later, they could do that, but they'd have to have more than 50% of the computational resources of the network, which is quite a lot of computational resources now. So it's pretty popular, so I don't know if you can see that. I don't really see that myself. I think it's 140 million there, somewhere around there. So this is transaction volume. How many transactions in Bitcoin's US dollars transaction volume on a day? These on sort of plotted over the months. So I think it's something like $100 million being traded on this kind of stuff every day. So it's pretty big, Bitcoin. Now, if you remember the original properties of money we talked about, it has to be scarce. You can't have too much money or you get the problems with post-war Germany or Zimbabwe, hyperinflation, so you need to limit the supply. It has to be trusted. There has to be ways in which people can check that the money that someone's giving you is the real deal. And in this case, we want to make electronic payments. So I have to be able to pay someone online using my currency. That's what we're looking for. So in case of gold, what limits the supply was nature. There's only a finite amount of gold. It's quite hard to get out of the ground, all the rest of it. And it's nature that also provides the way in which people can verify it. So Alice gives a lump of gold stuff to Bob. Bob can bite it, check its density, do some chemical tests. It's the nature of the gold that controls its authenticity or determines its authenticity. In the case of a bank, so the bank is responsible for limiting the supply of money, so you don't have too much of it. And the bank puts all these kind of anti-counterfeit measures into the notes, like the hologram, the bits of metal, the watermark, so that it's much harder to fake the money. So when Alice gives some cash to Bob, Bob sort of trusts it, or puts his UV pen on it, or do whatever tests the bank determines are appropriate for that particular currency. With a credit card, again, there's various checks on the credit cards, you know, the chips and the holograms, all this kind of stuff. And when you're paying money online, you just give off a bunch of numbers, and it's the bank that checks that those numbers actually correspond to, you know, Alice's bank account, and checks that the money's there and does all the, you know, verification of the transactions online. Now, Bitcoin is the computational cost that's limiting the supply of cash, and I'm going to explain how that works. And the computational cost is used as a mechanism for ordering the transactions in time, which is used to prevent double spending, which is used to ensure that transactions in Bitcoin can actually be trusted. So I'm going to explain all this in a bit more detail. Now, Bitcoins themselves actually don't exist anywhere. So there's no such thing as a Bitcoin. So, you know, it'd be nice to have a big chunky gold thing that was your Bitcoin, given they're worth about $300 or whatever. That'd be nice to have, but it's not the case. No physical object, digital file you can point to and say this is a Bitcoin. There's only transactions that transfer money from someone to someone, and then more transactions that transfer money to someone else. You know, you never actually, all you have is an address derived from your public key, and you've no way, and there's a series of records that transfer Bitcoins to that address. But it's just a series of records. It's not an actual physical thing or even a physical computer file, just records of transactions between different addresses with balances that increase or decrease. And if you want to work out how much cash, how many Bitcoins a particular address has, then you have to reconstruct that from the record of transactions. So let's start with the address. So each person has Bitcoin address, let's say, so they generate the public and private key, and the public key is hashed to produce the address for Alice and address for Bob. And there's no limit. It's not like a unique association here between the public key and Alice. Alice could have like 20,000 public keys if she wanted, right? You just generate the public keys, hash them, and then you have a Bitcoin address. So you can have a new address for every transaction if you want. Now let's talk about a transaction, because that's the sort of building block for the Bitcoin system. So suppose Alice wants to transfer some money to Bob. So what Alice does is she creates a message called a transaction. The transaction contains how much money is being transferred, Bob's address, and the previous transactions that transferred money to Alice. Then she signs this transaction, and then the transaction is the inputs, the outputs, and the digital signature. So let's explain that in a bit more detail. So this is the previous transactions, and the previous transactions would have been some input, like previous transactions that transferred money to Alice, that gives Alice the money that she's transferring. And then we have the output, who she's transferring the money to. So this is a previous transaction which had some input and transferred 3 Bitcoins to Alice, and that's signed by whoever transferred that money. We have another transaction with an input, a signature that transferred 4 Bitcoins to Alice, let's say. So firstly, these are the inputs. These are how much money Alice has, or where that money's coming from that she's now spending in the current transaction. So we have these previous transactions. Take the hash function. That's the input to the transaction. And then there's the output. This is Alice is now giving money to Bob in this case. So here we have Bob's public key, or address derived from Bob's address derived from the hash, which is the hash of the public key. And the output is like how much money we're going to give to Bob. And here's the change. So we've got in this case actually we've got 7 Bitcoins coming in, and she's spending 6 Bitcoins, and I'll explain what that means in a second. But there's a bit of change, there's a bit left over, and so the transaction needs to be zero sum, or if there's any missing, it ends up going to the, well, I'll explain all that later. So here we got the input, and there's a bit of change, and that bit of change goes back to Alice. So Alice produces this transaction with the input and the output, and she takes the hash, encrypts it with a private key, and signs it. So Alice is saying, this is I agree to this transfer of funds from my inputs to this output, and by signing it, she makes it tamper-proof and all the rest of it. So here's the new transaction. You've got the inputs, the money coming into the transaction, the money coming out to the transaction, and the signature that establishes that it was Alice that wanted to transfer this money. Now this difference between the inputs and the outputs is what's called a transaction fee. So if the inputs minus the outputs is greater than 0, then this amount goes to the computers that are doing the work to maintain the transaction records. So in this case, there's a transaction fee of 1 Bitcoin. So as I said, the input is 7 Bitcoins, and the output is 6 Bitcoins. So there's a Bitcoin missing, and if there's a Bitcoin missing, the computers that are processing the records get to keep that Bitcoin and add it to their own addresses. Now, Alice has done this transaction that's transferred some money to Bob. So how does Bob check that this is for real? Should he send the hat to Alice when he's received these 5 Bitcoins? Well, to check the transaction, you take the hash of the transaction, you decrypt the digital signature with Alice's public key, and you compare the hash of the transaction with the decrypted hash. If they match, the transaction's okay. So what Bob wants to check is that Alice is the one that generated this transaction, and we'll talk a little bit later about how he can check that Alice had the money that she spent in that transaction. But this is just checking that Alice actually signed the transaction and said that this transaction is okay. So here we have the usual stuff. We have the digital signature, the signature of the transaction. We decrypt that to get the hash of the transaction. Then we take a hash of the transaction and we compare them. And if the decrypted digital signature matches the hash of the transaction, then it was Alice who signed it, and it was and the transaction hasn't been changed or altered in any way. And this can be repeated and so on and so forth. So so as I said, it's just an indefinite change of transactions stretching back in time. So now we've shown you how you can create one transaction. Now I'll explain how Bob can spend the money that Alice has that Alice transferred to him. So here we have Alice paying Bob 5 Bitcoins. Now Bob's address is now associated with those 5 Bitcoins in this transaction. So then if Bob wants to pay 5 Bitcoins to Colin, he can use this input from Alice in the previous transaction, take a hash of that, make that his input to this transaction. So here he's got his 5 Bitcoins coming in, and then he's paying 5 Bitcoins out to Colin, in this case without a transaction fee, and he does exactly the same thing Alice did. He takes the hash of the transaction, encrypts it with his private key, and that's his digital signature, and so on and so forth. So you just got chains and chains of transactions transferring money from one person to another, to another, to another, and the total amount that ends up associated with an address over this entire chain is their current amount of Bitcoins. And you can only find out how many Bitcoins is associated with an address by reconstructing the history, by looking through the entire history and figuring it out, which isn't hard to do, but you've got to do it. So yeah, here we have, so Bob's signing the transaction, and so this is a new transaction with an input, an output, and the digital signature, and we can just check it, and Colin can check that in exactly the same way as Bob checked the previous transaction. It's possible to use multiple addresses, so Alice, being a bit of a dodgy girl, has 2 sets of public-private keys, so 2 accounts. She creates a transaction from both of these addresses by signing the transaction with both private keys. So in this case, you've got one transaction that transfers money to this address of Alice's, and another separate transaction that transfers money to a different address also owned by Alice. And what she does is use these 2 transactions as input, transfers money to Bob or Colin, whoever, and what she does in this case is she signs it with both private keys. So she, in this way, demonstrating that she owns these 2 sets of Bitcoins. And if you're talking about later, I'm going to talk about privacy. In this case, it's showing that she owns both of these coins. So in this kind of transaction, there's a link made between the 2 sets of private and public keys. Right, so that's how we do transactions. This is how Alice sends money to Bob, Bob sends money to Colin, so on and so forth. But now we hit the double spending problem, and Nakamoto's original paper was sort of framed partly around this double spending problem. So we want electronic currency that we can spend online that's without a trusted third party. So classically, when I spend money online, it's the bank that checks that I have the money and that I'm transferring the money to Bob or Alice or whatever, and that it does the actual transfer. And because both parties trust the bank, this all works. But in this case, currency is just an electronic document or file, right? Seems that I can buy something from one person using my electronic currency, and then buy something from someone else using a copy of that currency, right? So how do we check, firstly, that Alice has 7 Bitcoins to begin with? And what if Alice issues 2 transactions, one transferring 5 Bitcoins to Bob, and another transferring 5 Bitcoins to Colin with the same input? She spends the same money twice. That's what's meant by the double spending problem. So here we have her using this set of inputs to spend, to give Bob 5 bitcoins, but she could use the same set of inputs, is that right? Yeah, same set of inputs to give the same 5 bitcoins to Colin. So she spent the same money twice, giving 5 bitcoins to Bob, 5 bitcoins to Colin, and Bob and Colin, one of them's the loser, right? And she could just do this indefinitely. So to address this problem, we have this idea of a blockchain. And this works in the following way. So we've got these various transactions, all this kind of stuff. This is the transactions I've just explained. And these transactions are recorded in blocks. And each block contains a hash of the previous block. That's the neat thing about it. So you've got one block, you take a hash of that block and include that hash in the next block. And so in block 2 contains the hash of block 1, so block 2 must have come after after block 1. And then block 3 contains a hash of block 2. And so you get this determinate ordering of time of the blocks because each block contains the hash of the previous block. So the hashes are one way, so the transactions in the second block must come after the hashes in the first block. So then you've also got the stuff that if you change the block, you change the hash value, and you're going to break the chain. So if the chain's valid, then the transactions that are in each block are ordered in time. That's the idea. Ordered between blocks, not ordered within blocks. This gives us the order in time. So here we have the transactions. Sorry about the resolution of this. So this is the first block here, and we've got all these transactions in this block. And then we take a hash of that, the entire block, and include that in the next block. And the next block has another set of transactions. So this transaction must have come after this transaction because this block contains a hash of this block. So you couldn't generate this block without this block, so this transaction must have come after this transaction. And if you change this transaction just a tiny bit, you're going to change this hash, change the hash of the block, and so so this block's no longer going to be part of the blockchain. There's going to be a mismatch here between this hash and the actual hash of the block. So it's very easy. Hashes are dead easy to, they're computationally light to execute, so you can very easily check that the hash of this equals that, the hash of this equals that, and therefore you can check that this transaction came after this transaction, which came after this transaction. So that's how we can order that's how the transactions are ordered in time, through this blockchain. And there's been various discussions at Middlesex and elsewhere about how you can use the blockchains in many different ways. But this is, in Bitcoin, the blockchain is used to order the transactions in time. So that if Alice gives Bob 5 bitcoins here, and then tries to pay 5 bitcoins to Colin here, it's easy to see that she's already spent the bitcoins previously, so that this transaction would be invalid. Now, how do we create this Bitcoin in a way that we can all? How do we create this blockchain in a way that we can all agree on it? That's the next problem, because my version of this Bitcoin might include Alice giving 5 bitcoins to Bob, and another version of this could include Alice giving 5 bitcoins to Colin. But we don't want to use a bank for this. We don't want to use a trusted third party. We want to use a peer-to-peer method. The peers are the ones who should be collaborating to verify the transactions and agreeing on the correct ordering of the blocks. And this must be done in a way that's resistant to attack and fraud. A solution to this is use a computationally demanding task that's called a cost function. So each of the peers, so the blocks are generated by executing a function that's difficult to compute but easy to verify. That's the crucial thing. You don't want a function that's difficult to compute and difficult to verify, because that will waste everyone's time. You want something that's hard to compute, so it's hard to extend the blockchain, but easy to check that the blockchain has been extended. And that's what I'm going to explain about now. So the cost function is to look for a value that, when hashed, for example with SHA-256, begins with a given number of 0 bits. This is the partial hash collision that I discussed earlier. And the work that's required to do this is exponentially related to the number of 0 bits. And you can verify this just by doing a single hash. So it's hard to find a value that starts with a given number of 0 bits, but it's very easy to check that you found that value. So a simplified example, suppose we've got so we have a string here. I have a string and a number. So this is a simplified example of how it works. So this string could be anything, could be the cat sat on the mat, whatever you like. And we're going to take a hash of the entire string combined with a single number. So we're going to do hash of the string plus 1, and let's suppose it leads to that. And this is hash as 1 leading 0. And then suppose we change the number to 2. We increase the number, leave the string exactly the same, do a hash of that, the string plus the number 2, and then it has 2 leading zeros. And the task is to find a value of number that we add to the string and gives a hash with a specific number of leading zeros. Okay, well, I hope that's clear. So that's how we extend the blockchain. I'll give you a concrete example in a second. So how this works is that new transactions, so people are off there spending their bitcoins, and then they broadcast the bitcoins, their transactions to all of these nodes, all of the nodes that are participating in the network. The nodes communicate among each other to find the longest existing blockchain, so which is the longest chain that's already out there. And then the first thing the nodes do is they check the transactions against the blockchain to ensure they haven't been spent. So they look at the addresses, they track the addresses back through the blockchain, they ensure that the money is there and the money hasn't been spent twice or whatever. So they check that all the broadcast new transactions are valid. That's done by all of the nodes that are participating in the network. Then they get a bunch of the valid transactions, put them together in a block, and then they want to find a new block that solves the cost function. So they want to add a new block that contains all the valid new transactions. So they create a new block, and this new block contains all of the new valid transactions that they've checked, because they're not going to get anywhere by including invalid transactions because the other nodes won't accept it. It's a peer-to-peer system in which they're all checking each other. So they take a hash of the most recent block. So the new block contains all these valid transactions, the hash of the previous block on the longest blockchain, and a number called a nonce, and that's similar to this number here, which I'll explain. And they look for a value of this number, or the nonce, that leads the hash of the block to start with the required number of 0 bits. And you can only do this search systematically. There's no shortcuts. You've basically got to do a hash of this new block with the nonce set to 1, a hash of the block with the nonce set to 2, and so on and so forth. And this is hard and takes a long time, and the time required depends on the number of 0 bits you're looking for. So this is the sort of same story in pictures. So as I said, it's a blockchain. So here we have the hash of the previous block. Here we have all the new transactions, which we've checked are all valid, that the money exists in this, and Alice has this money because we've checked all the previous transactions, and so she can actually transfer that to Bob or to Colin or to whatever. And then we have the nonce here, this number that we're going to increase systematically until we find a value of the hash that has a certain number of leading zeros. So we build our block, and then we start looking for a value of the nonce that leads to the appropriate number of leading zeros. So we take all of that, bung it through the hash function, and find out and get the hash of the block and see how many leading zeros there are. In this case, there's 2 leading zeros. Then we increase the nonce to 2, take the hash of everything, and bad luck, we're down to 1 leading zero there. Then we take another hash of the block, and we're even worse off now. It turns out that it's got no leading zeros, right? With the nonce set to 3. Now we set the nonce set to 4, and we get lucky here. Turns out that the hash of this entire block, when the nonce is set to 4, gives us these 4 leading zeros, and success, hooray, off we go. So we now know that the hash of the block. So we now found a block that's completely valid, meets all the criteria, and we can then broadcast that to the other nodes. So what we've done here is we've extended the chain by finding an appropriate value of the nonce, and then we can broadcast this as our new block to the rest of the nodes, and if they all accept it, they all think it's valid, then they'll add that to the chain. That'll become the new longest chain, and then everyone will start working on the next block and the next block and the next block and so on. So nodes are competing to find a solution to the cost function for this block. When they've found a solution, the new blockchains broadcast to all the other nodes, and if all the transactions are valid and not already spent, if the nonce is correct, does lead to the correct number of leading zeros, then we've added 1 block to the longest chain, we've extended the blockchain, and then all the nodes start working on the next block. So that's how it works. And what controls the supply is that solving this cost function takes a lot of computational power. You've got to systematically work through an awful lot of hashes in order to find one that has a required number of leading zeros. And people are motivated because the nodes that extend the chain, the ones that solve this computational cost problem, are rewarded for their work. So the first transaction in a block starts new coins that are owned by the creator of the block. So they've got like special transactions here that give the person who creates the block a certain amount of bitcoins. And miners also pay the transaction fee that's taken out of the transactions in the block. So when there's a difference between the inputs and the outputs, that difference can go to the person who creates the new block. And this is called Bitcoin mining. And there's quite a few Bitcoin mining companies out there using thousands of specialized hardware boards or maybe cloud data processing to figure out the solution to the cost function and to extend the blockchain. So these typically like large warehouses, they put them where land and electricity are cheap, and they can make millions of dollars per month if they get everything set up right. And I think there's quite a lot of large Bitcoin mining companies in China, but there's also some in the States. So this is like Washington, D.C., I think. You know, the Washington State, I always get mixed up. And as you can see, these are like highly specialized boards that are dedicated to just solving this one computational task, racks and racks of the thing, and you know, you can make a decent amount of money when you've set your rig up right if electricity is not too expensive. Now, to fine-tune the system, the idea of the system is that they generate one block every 10 minutes, I think, something like that. So they're doing a little bit of subtle changing to the cost function to match up the available computer power. So, you know, this is the computer power now, but when the system started, it was, you know, a few computers, you know, running standard hardware. So they want to keep issuing new blocks at a nice steady pace. You don't want it too hard, or you won't be incorporating new transactions fast enough, and you don't want it too easy, or maybe there won't be enough transactions to incorporate. So every 2016 blocks, they recalculate how many leading zeros need to be found to generate a new block. So they measure how fast the previous blocks are mined and then adjust the cost function appropriately. They're also adjusting the reward function. So they're generating blocks at a steady once every 10 minutes. There's also, I think, been some recent issues about who controls the Bitcoin network in terms of if you control lots of the resources in the network, you can dictate some of the policies. And they wanted to fiddle around with I think it's increasing the number of transactions in a block, something like that, because they were, you know, the system hasn't got enough capacity to process all the transactions that are being generated now. So there's a few issues with Bitcoin at the moment. Anyway, so limiting the cost function to get these blocks every 10 minutes, and then also limiting the reward, changing the reward function over time. So it's 25 Bitcoins. Originally it was 50 Bitcoins, currently it's 25 Bitcoins, and every 4 years, roughly, the number of Bitcoins that can be mined reduces by 50%. So it's limiting the number of coins in existence to a finite amount. The important thing is, if you're a malicious user and you just take the longest blockchain and you knock up something that doesn't match these rules, then none of the other nodes will accept it, and so you can't, you know, they just ignore the new block that you've created. So that's why the peer-to-peer mechanisms function, that all the other participants in the network are checking what the person who's created the new block has done and making sure that it's correct. So this decreasing cost function, or decreasing reward, means that no more than 21 million Bitcoins will ever exist. And it's got like the rate of issue of Bitcoins designed to slow to zero, so there's no more than 21 million Bitcoins ever. So maybe it's just a limited supply, something like that, I'm guessing is the reason for changing the reward over time. Right, so if you're a user of the Bitcoin system, you probably have something like a Bitcoin wallet, and that holds your Bitcoin addresses and the public-private keys that you own. You know, so you can have as many of these as you like. They don't have any personal data in them. The only thing that the Bitcoin address has is your public key, the hash of your public key. And so using the wallets, you can work out by looking at the previous transactions how many Bitcoins you actually have associated with these public-private key pairs. You can generate new public-private keys, carry out transactions, and your Bitcoin wallet could be on a website, maybe you have local software, and you could even write it all down if you wanted. Now, the security of the system comes from the fact that you can only extend the blockchain if you expend considerable computational cost. So all the other nodes are only going to work on a blockchain that's valid, you know, a blockchain in which transactions that spend money are spending money that comes from previous transactions or that was generated when the block was generated. The previous nodes are only going to work on a blockchain whose hashes all match up, right? The hash of the second block, the hash in the second block corresponds to the hash of the first block, and so on, so that the blockchain is correctly ordered in time, that it hasn't been tampered with in any way. So, yeah, because you don't want to waste lots of computational effort on a blockchain that's incorrect. You're not going to waste your time extending an invalid blockchain because you know that eventually someone's not going to accept it. You're only going to spend your time and your money extending the blockchain if it's a valid blockchain. That's the point of the computational costing. So if you wanted to compromise the system, what you're going to need is more than 50% of the computational resources in the system. So if you have more than 50% of the computational resources in the network, what you can do is basically make a second copy of the blockchain in which you could insert your own false transactions or whatever. So you could build your own blockchain, a fake blockchain, but you're going to need an awful lot of computational resources to do that because you're going to have to recalculate the cost function for each of the blocks. So if a majority of the CPU power is controlled by honest nodes, then the honest chain is going to grow faster and outpace competing chains. So if you want to change a previous block, change a transaction, you're going to have to recalculate all the blocks that come after that, solve the computational cost function for all of those blocks, and that's going to require a huge amount of computational power. And the motivation for doing this is not that high, right? Because if you've got this amazing computational power, all these computational resources, then you can also make legitimate money by extending the blockchain anyway. So you could just make money by extending it. Why go to the trouble of modifying a past transaction when you can just extend the current blockchain and make money? There's a potential for conflict, right? So nodes take the longest chain to be the correct one and keep on working on extending it. Now it's possible that two nodes broadcast different versions of the next block because they happen to have different transactions available to them. And in this case, they'll work on the first chain they receive, keep extending it, and keep the other branch in case it becomes longer. And then when the next block is added, only one branch will become longer, and then all the nodes will switch to working on the longest branch. So there might be equal nodes, equal branches with different blocks on the end, but then one will get longer, and then the nodes will just focus on extending the longest blockchain. And this is because new transactions might not reach all nodes, networks, whatever. As long as they reach lots of nodes, they'll end up in a block because each block is gathering together a bunch of the transactions they receive, putting them together and extending the chain. So as long as they get to some of the nodes that are actively working on extending the chain, they'll eventually get incorporated. And if a node doesn't receive a block for some reason, then they can see it's missing because they can see later versions of the chain and they can just request it. To save disk space, you've got like the full blockchain with all of the transactions, but you've also got a sort of compressed version of it in which the transactions are hashed in a Merkle tree. Or rather, you can get just the hashed version, or you can get the version with the full Merkle trees. So Merkle tree, so Merkle tree looks like this. So here you have like the data blocks, which could be correspond to transactions, and then you've got a hash of these data blocks here, which are going to be these are first level compression, and then you're taking the hash of two of the hashes to create another hash here, and then you're getting a top hash, which is the hash of the top hashes here. So with all this sort of hashing, meshes with the brain after a while, but these are basically hashes of hashes of hashes, and they're storing top hash. So this top hash being a cryptographic hash and all the rest of it, even a small change here to the data block would change the hash here. So there's only one Merkle tree that corresponds to that particular hash. So the transactions are hashed in the Merkle tree, and only the root is included in the block's hash. So actually, the block only contains this top bit, the root hash. It doesn't contain all of the transactions because there could be quite a few transactions in each block. And then you can do a bit of pruning to discard all transactions, but also more importantly, you can also the block itself can just be the blockchain itself can just be stored as all the root hashes, and then for most of the nodes this is fine. And then then some nodes can store the entire Merkle trees, and the other nodes can check that this is the correct Merkle tree by checking the root hash, which is stored, throughout the entire system. So most of the nodes only need to store this top-level data, but at least some of them need to store the more detailed data so that they can check and they can check that that data is valid by looking at the hash of that. I think that's it on the. And you can also potentially prune out some of these things by, if you know that Alice transferred a Bitcoin to Bob and Bob transferred a Bitcoin to Alice, then the earlier Bitcoin transactions can be pruned, but if you're dealing with fragments of coins, this becomes a bit more tricky. Right, so Bob receives these 5 Bitcoins from Alice. I've given you the full picture about the blockchain, how this works. Now I can explain how Bob checks that he's actually received these bitcoins from Alice. So what Bob does is he queries the other network nodes to obtain the block headers of the longest proof of work chain. So that he obtains these block headers. So he gets the longest chain, which consists entirely of these block headers. Then he requests the Merkle branch that links the transaction to the block that it's included in. So then he fishes out, he's got a transaction from Alice that he wants to check, and so he gets the Merkle branch. He knows that when Alice made this transaction, whatever, so he can find out he can get the full transaction, you can get the transaction that corresponds to the particular block. So you can request from the machines that hold the full blockchain, you can get this particular Merkle tree and find the transaction that transferred the money to him. Let's suppose it's TX3. And so you can see that this transaction has been incorporated into the chain by the network as a whole. So if you can get this if this transaction has been incorporated in the blockchain, then that means that this money here that's been transferred to him has not been spent twice. It's valid. It's been accepted by all the other nodes working on the system, who all are very invested in this system being accurate and correct. And so you can tell that this transaction has been included in the blockchain, and therefore that it's a valid transaction that's not spending money that doesn't exist in Alice's account. So he can be pretty confident if he finds this in the Merkle branch of a block that's been incorporated into the chain that transaction is valid. So just touch on privacy. So Bitcoin's kind of quite well known for being private, and it's mostly private. I think it's the most accurate way of saying it. So Bitcoins are linked to public keys, not to individuals. So all the money, all the transactions are transferring money to and from private keys, addresses, Bitcoin addresses, which are the hash of the public key. So there's no link between a person's name, address, telephone number, whatever. There's just a public-private key pair. So you can receive money if you've got a public-private key pair without disclosing your identity. And you can use a different public-private key pair for each transaction. The only tricky thing is that multi-input transactions show that the inputs have the same owner. So if you remember this, so here Alice has one receiving money here, and spending that money and having a transaction that involves both of these public-private keys. And this transaction shows that Alice owns this key and owns this key. So this become a little bit problematic. And also the other thing you can do is you can trace the history of transactions back through the blockchain, right? That's the feature of the thing. So you know that this transaction followed another transaction, followed another transaction. So if you can trace that this Bitcoin was spent 20 years ago, let's say, on Silk Road to buy some dodgy substances from Alice or whatever, then you can tell that Alice is then using that same Bitcoin that same address to spend money, and that's combining with some other address that she might have received from legitimate business or whatever. So if you can link if you can link in some other way the transaction to a purchase of goods or laundering money or whatever, then you can see that being combined with another address, then you can tell that there's a link, but you can tell that it's the same person. Now, if you lose the private key, you lose the money. So same as gold and cash, right? If you lose 50 quid on the street and someone picks it up and takes it, it's gone, it's gone. So there was this, in February 2014, Mt. Gox exchange, this is like a leader in Bitcoin trading, went bankrupt, and hundreds of millions of dollars worth of Bitcoins went missing. The files went missing, someone nicked them, who knows? But it's just like cash. You can just lose, if you lose the public-private key pair, you've lost the Bitcoins, end of story. But the Bitcoins of other exchanges, rates of other exchanges remained high, so it didn't kill the system because it's like cash, right? You're not going to abandon gold because someone loses some gold in the sea, right? So Bitcoin's criticized for high volatility. Volatility just means that its price, its exchange rate with other currencies, or its price varies quite a lot over time. So this is the volatility of Bitcoin. So it sort of varies and comes up quite high volatility. I don't know enough about economics to know what 15 volatility mean, but it's got high volatility. This is kind of a good thing if you're a stock trader or a Bitcoin exchanger, because you can make money much faster if there's much more higher fluctuations in the price. It's got exchange rate with US dollars, so about $300 per Bitcoin, I think. So it's got quite a high value, sometimes very high, but then it varies over time, like all these things. Other factors in the marketplace, confidence, all the rest of it. So Bitcoin was the original, the first really successful cryptocurrency. and then there'll be a lot of them come since, and other applications of the Bitcoin have been proposed, of the blockchain have been proposed. And so I think maybe three of the essays and class presentations are on some of the other cryptocurrencies. Okay, so this lecture, it's been an overview of cryptocurrencies with a focus on how Bitcoin works. Next lecture, we're going to go into some of these enterprise technologies, starting off with remote procedure calls and remote method invocation.